Hey there, chemists. Okay, we're going to put all of our reaction skills together today and apply them to synthesis problems. We've got a number of synthesis questions to tackle on our worksheet today. I'll walk us through the first half of them, and I'm actually going to have you do the rest for homework. So I'm just going to go through the first batch of this one, and then we'll tackle the problems on the back of this in another video. With any synthesis problem, when they're so open-ended like this, it's always a good idea to think backwards and start with a retrosynthesis. So I want to make a carboxylic acid. How can I make a carboxylic acid? What functional groups can I use? Going back to the reaction summary we just did in the other video, there's many ways to do that. You can make a carboxylic acid from the oxidation of a primary alcohol. That's with the Jones oxidation. I'll write a few others just as some options. You can make a carboxylic acid from the KMNO4 oxidative cleavage of an alkene. That will cut right through that carbon-carbon double bond, and you'll oxidize it to an acid. I'm considering lots of options here. You could make a carboxylic acid from a Grignard. That's one carbon less, and add a CO2 molecule to it. That would take a 5-carbon piece, add 1, and you would get a 6-carbon piece. Actually, when I look at our starting material, I notice that we have 4 carbons, so I like the idea of adding carbons, but I don't think this is the way to do it. So I'm going to erase this one already because I feel like this is not the best approach. We could get it to work, I'm sure, but it might just be steppier than some of our other options. There is another way using a Grignard, and it doesn't add 1 carbon. It would add 2, but that would make an alcohol, and we're gonna get back to that. More recent chemistry, we could make acids from esters, but I'm actually also going to get rid of that because as soon as I draw the ester and I think, how do I make an ester? Esters come from carboxylic acids. So I would just be back and forth between the acid and the ester, and that doesn't make a whole lot of sense at this point. And considering the alkene and the alcohol starting material, I'm going to stick with the alcohol, not just because I drew it first, but because we know a lot more chemistry about alcohols than alkenes at this point. So let's consider how we make the alcohol. You can make an alcohol from the oxidation of a carboxylic acid, but that obviously doesn't make sense here, so let's think about something else. Speaking of adding carbons with Grignards, you can make an alcohol by adding 2 carbons to a Grignard. Anybody remember what little building block will give us an extra 2 carbons? It's an epoxide. So if I throw in an epoxide with a Grignard, you add 2 carbons and you would change your 4-carbon piece into a 6-carbon piece. So I'm liking this approach a lot because we get back to a 4-carbon building block. Now, Grignards are great because once you get to that, you go, how do you make a Grignard? There's only one way, from the halide. There's a couple of ways to make halides, but a good one is to make it from an alcohol. So I'll write that. And alcohols can be made from carboxylic acids. So we can get back to our starting material. Now we just have to write this out in a forward direction, but there's our retrosynthesis, going back one functional group at a time and drawing the appropriate intermediate that we would intercept, or the appropriate molecule that we would make along the way. So let's write it out in the forward direction. Starting with our carboxylic acid, we're going to first reduce the acid down to an alcohol. That's with lithium aluminum hydride. I always find it helps to write out the transformation first and then fill in your reagent after you remind yourself of what you're trying to do. We want to turn that alcohol into a bromide. What reagents do we use for that? Phosphorus tribromide. This is a primary alcohol, so we don't use HBr. We'll use PBr3 instead. That's better for less substituted alcohols because there's an SN2 element to the mechanism. To make the Grignard, we turn the bromide into the organometallic. That's just magnesium metal. And then to react the Grignard with an epoxide, maybe this is the hard one to see. Grignards almost always require some type of acidic workup. What you'll get is a primary alcohol with 2 extra carbons. You can remind yourself of how that works if you want. The organometallic is nucleophilic at the carbon attached to the metal. It forms a bond with the epoxide carbon. The epoxide opens up, so that's how you get a total of 6 carbons. And that oxygen, which is an anion at first, becomes an OH with addition of H+. Lastly, we turn this into our acid. You can use the Jones oxidation. Chromium oxide and water will get you to your carboxylic acid that we're asked to make. Okay, so there you have it. 1, 2, 3, 4, 5 steps from starting material to the acid product. Let's try the next one. Next one is a 4-carbon alcohol to a slightly larger ester. Esters, we actually just reminded ourselves, are often made from carboxylic acids. So you draw what looks almost like exactly the same thing, just change what's changed. This is an OH. You'll bring in ethanol to make the carboxylic acid. We'll do that in the forward. How do you make carboxylic acids? Well, we could make them from alcohols and all the things we just went through, but I'm noticing now this is 1 carbon more than the starting material. 1 carbon more. So how do I add 1 carbon? We just said it, CO2. That's what we decided to not use up above. We're going to use it here. Carbon dioxide will react with a Grignard to make a carboxylic acid and add that extra carbon. How do you make a Grignard? Start with a bromide. How do you make a bromide? You make it from an alcohol. And when you do the reaction with PBr3, there actually is an inversion of stereochemistry with PBr3 because it's SN2 related. So we actually get the inversion of stereochemistry, whether you noticed or not, that we want in this reaction. And there we have it. We've got our whole retrosynthesis. Let's write it out in the forward direction. So forward, starting with our alcohol, happens to be chiral. I'll first react it with phosphorus tribromide. That will invert the stereochemistry and give us a bromine. Then magnesium metal will turn it into a Grignard. Then we can react it with CO2, followed by an aqueous workup. That will give you 1 new carbon, and then that carbon becomes a carboxylic acid. Lastly, we have to turn that into the ester product. Stereochemistry stays the same for that part. I'll use the Fischer esterification, ethanol, and H+. Alternatively, you could turn this into an acid chloride and then turn it into the ester. That probably works a little bit better. But with such a simple molecule, this should be robust. 4 steps, and there we go. Okay, let's do one more, and then I'm going to have you try the next one before I show you the solution, and then the remaining batch will be homework. The next one is an amide. So how do you make an amide? If we go backwards, there's really only a couple of ways to make an amide. In this case, I'm also going to check my carbon count. We have 3 carbons in the beginning, and we actually are adding a carbon, so I'm thinking of 1 carbon building blocks. Amides come from some type of carboxylic acid derivative. You actually can make them from a carboxylic acid and the amine, and in this case, it would be a primary amine in the same molecule. That's how you make the carbon-nitrogen bond. That doesn't react on its own, but we just saw in a class quiz not too long ago how the reagent DCC acts as a coupling reagent to make that amide bond, so we'll try to use that for this. Now, how do I make a carboxylic acid or an amine? Well, we already have a carboxylic acid in the starting material. The question is, how do I turn the alcohol into my amine and add a carbon while at the same time carry this carboxylic acid? So we need some mild reagents for this. If we make the amine by reduction of a nitrile, that's a mild enough reaction that we can probably carry the carboxylic acid. And nitriles, the cyano group, are great 1 carbon building blocks, just like CO2. So we could potentially make this nitrile from a bromide like that. And hopefully we can easily make that from our starting material. So let's go to the beginning, and let's take our hydroxy acid. We'll brominate the alcohol. And then we'll do a substitution with a cyanide source. Hopefully we'll do a good SN2 on that bromide. And then a great way to make a primary amine is hydrogenation, H2 and palladium. We'll take that carbon-nitrogen triple bond, turn it into a carbon-nitrogen single bond. And then lastly, how do you couple these two things together to get the nitrogen to form a bond with the carbon and get your 5-membered ring? One reagent is DCC, dicyclohexylcarbodiamide, which is a coupling reagent. I think I'm remembering that correctly. And then you can get your cyclic amide, which is called a lactam. So a little bit shorter, 4 steps. Okay, let's try one more together in this video, but I actually want you to hit pause and see if you can come up with at least a little bit of a retrosynthesis for this one. This is an anhydride. Ask yourself, how do you make an anhydride? There's really only one way for our purposes. So what's a couple of backward steps from that? And maybe at the same time, what are some forward possibilities of your bromide? Try that now. Okay, let's see how you did. So the anhydride is sort of a double ester, and it really comes from something that's similar to our Fischer esterification. 2 carboxylic acids can come together to make a cyclic anhydride in this case. They lose water. It's not a very pretty drawing, but that hopefully gives you the idea of how this happens. One of them attacks the other in a substitution reaction. How do you make a carboxylic acid? You can make it from the hydrolysis of any carboxylic acid derivative. We said that when we were looking at carboxylic acid derivatives in the beginning. I could just put an X here. But like, what kind of carboxylic acid derivative can we use? So let's check back at the starting material. We've got bromides, so we can do substitutions on those bromides. We've also only got 3 carbons, and I notice I need 5 in the end. So we were just reminded that cyanide is a great single carbon source, and it can do SN2s on bromides. So what if we started with our bromide and did a sodium cyanide substitution twice, times 2. That would give us a double nitrile, which is a carboxylic acid derivative, and which under hydrolysis conditions will give us 2 carboxylic acids on either end of a 5-carbon chain. And then we can cyclize that. All you have to do to get this to cyclize is actually just heat it up. That would involve one of the oxygens attacking the carbonyl of the other. Actually, in all likelihood, it's the carbonyl oxygen that does it, but then you get some proton transfers. It'll look like this oxygen bonds with that, and you lose this OH. So I'll draw it ugly first. So just you can see how it forms. We'll have that. That actually is the product. That's a 6-membered cyclic ring with the anhydride in place. Okay, so there's 4 of the syntheses on this set of notes just to get you started. There's 3 others that I'd like you to try for your homework, and then you can check the solutions and see how you did.